So we're going to start in section 4, large systems. Up till now, we've been dealing with things where we have a small countable number of components, particles, or oscillators for the system. The trouble becomes that the multiplicity gets unbelievably large once we get beyond just a handful of these. So we've got to figure out how we're going to deal with the numbers when we get up to these large systems. We plotted out already the multiplicity as a function of, well, let's say we're dealing with the amount of energy contained by maybe one of our two systems that are exchanging energy back and forth. The multiplicity, if we've got a very small number of oscillators, let's say we're dealing with an Einstein solid. Multiplicity has a peak. Let's say if we have the quanta of energy, the number of units of energy by system A, if it's exchanging it with B, and there will be some peak right around here. But if you have more units of energy and you have more oscillators to deal with, this peak becomes more sharply peaked. The larger your system is, the sharper that peak is, the narrower it becomes, which means that you are much more likely to find the combined system right near the most likely point. For small systems, there's a decent chance of finding it on one side or the other of that most likely point, but for the larger systems, you're almost never going to find it outside a very narrow range there. Okay, so how do we deal with the numbers when we get into these very large systems? We've got to make a distinction between small numbers, large numbers, and the appropriately named very large numbers. Okay, small numbers are things that we could write down with normal notation. 5, 100, 3,000 maybe. Those are small numbers. Small numbers behave the normal way that we're used to dealing with, adding them, subtracting them, dividing, multiplying. Regular numbers. But large numbers, these are numbers that we would more conveniently write with exponential notation. So 5.7 times 10 to the third power. Now, of course, I've really made a bit of an overlap here. I wrote 3,000 up there as a small number, and maybe that's stretching a bit much. But once we start writing numbers in exponential notation, once we need to start writing them with that, all right, now we're dealing with large numbers. What about 10 to the 42nd power, or our most useful large number, Avogadro's number. So if we have something on the order of a mole of some substance, we've got something on the order of 10 to the 23rd power of this. Okay, it's within an order of magnitude. Now, the thing about large numbers is that you can add a small number to one of these without really changing the large number. Of course, we're dealing not strictly, truthfully, we're dealing with estimates. But if you've got 6.22 times 10 to the 23rd power and you add 5 to it, we don't have the level of precision needed to bother with that 5 because we have 23 zeros following this. And we just simply are not down to that level of precision. So the special property of large numbers is that you can add or subtract a small number from them without changing them. That's the key thing. So, for example, 42 plus 10 to the 23rd power is still 10 to the 23rd power. Same thing if we subtracted 42 from it. There is one exception though. If we are eventually going to, let's say I've added 42 plus 10 to the 23rd power. If I'm planning to then subtract 42 from that again, I need to, I'm sorry. If I started with 42, if I add 10 to the 23rd power and then I'm going to subtract 10 to the 23rd power, I do have to keep track of that. So 42 plus 10 to the 23rd minus 10 to the 23rd is still 42, not 0. That's the exception. We got to keep that in mind. Make sure there wasn't anything else I should do. Okay, so really to define, now because I'm going to go on to an even larger set of numbers, note that large numbers, should have said this up front, large numbers are made by exponentiating small numbers. So in the exponent we have a small number. Okay, which brings us to the next one. Very large numbers. These are made by exponentiating large numbers. For example, 10 to the 10 to the 23rd power. These are ones we haven't really dealt with much before in many other classes. Note that 10 to the 10 to the 23rd power is 10 raised to 10 to the 23rd power. Don't confuse it with 10 raised to the 10th power and all of that to the 23rd power. That's different. So 10 raised to this large number. Okay. The special property of very large numbers is that you can multiply them by a small number and not make any change. Actually, sorry. You can multiply them by large numbers without changing them. So 10 to the 10 to the 23rd power times 10 to the 42nd power is still just 10 to the 10 to the 23rd power. Why is that? Because let's see. I see that that's off the edge of the screen here. So 10 to the 10 to the 23rd power times 10 to the 42nd power is 10 raised to the sum of these two exponents. 10 to the 23rd plus 42. And what have we said about, let's see, the numbers in the exponent there. These numbers, that's a large number plus a small number. And we've already said that a large number plus a small number is just the large number. There. So by taking a rule that we already knew from math, and this special property about adding large numbers and small numbers, we can see that very large numbers we can multiply by large numbers without changing them. Once again, there's an exception. If we intend, if I've got 10 to the 42nd power, if I multiply it by 10 to the 10 to the 23rd, but I'm then intending to divide it again by 10 to the 10 to the 23rd, then I've got to keep track of that. Okay. So if you're going to divide by the same very large number, then you have to keep track of it. Okay. Very large numbers are not things we're going to deal with a lot directly. What's going to be common is that we will take the natural logarithm of them very often, or the base 10 logarithm, either way. but we're often going to take the logarithm of these so that we can use just the exponent, which is merely merely a large number. And at the end, when we want to get back the very large number, then we simply exponentiate, and we've recovered it. So it's going to be easier to deal with the logarithm of these than to deal with these directly. This is going to be a common trick. Okay. Now, let's use some of this. Something that's going to be useful with these large and very large numbers is called Stirling's approximation. Okay. Stirling's approximation says that for n much greater than 1, n is some number, n factorial is approximately n to the nth power times e to the minus nth power times the square root of 2 pi n. Okay, so we have three terms here. I'm not going to derive Stirling's approximation, although you can find the derivation of this. And in fact, it is in Appendix B3 on page 389. Okay, so it can be derived, but I don't need to bother with it here. We're simply going to use it. And I'm going to show that we don't even need to use the full version of this. We can often get by with large and very large numbers with one or two terms on it. Okay, so in many cases, we don't even need this level of precision, and this is already an approximation. So we can approximate even further. So, if n is a large number, as we've defined it already, then n factorial is a very large number, because we're multiplying a whole long series of large numbers. Okay, so n is a large number, something that's exponentiated. N factorial is a very large number. So, if we take this first term, n to the nth power, that's very large, times e to the minus, let's see here. Oh, n to the nth times e to the minus nth. That's very large, because we're exponentiating a large number. But then we've got multiplied by the square root of 2 pi n. Well, n is merely a large number, and the square root of it is merely a large number. You can probably barely read that, but I've just written very large for the first two terms times a large for the second term of the third term. So, remember that a very large number times a large number is just a very large number. Okay, so if n is a large number, then we can really just take the first two terms here, and that's going to be good enough. Furthermore, as I said, since this is a very large number, we are often going to be dealing just with the logarithms of these very large numbers. And since we have an exponential here, probably best to use the natural logarithm. That comes out nicely. So, let's take the natural log of both sides. When you've got the natural log, in fact, I will just say log without specifying natural. Most of the time, if we take the log in this class, it's going to be the natural log, and we can just follow along with whichever one to pick. Whenever you've got the log of a product, it winds up being what?
Separate the natural logs and then add the other.
Right, so it's going to be the sum of the log of the first term and the log of the second term. So that's nice for breaking these up because we see that we've got an exponential. The exponential number is one of these two. It'd be nice to take the natural log of the exponential because then we just get the exponent. So it's log of n to the nth power plus log of e to the minus nth power. What can we do when we've got log of some argument, we'll call it, raised to an exponent? Right. So we can take, for log of n to the nth, it's n times the log of n. Here, we've got log of e to the minus nth power. Well, log of e to anything, natural log, is just that exponent. So we have n log n minus n. Make sure I've got that right. Yes. And this is really still an approximation, so I'll put that in there. Again, so if n is large, we found that n factorial is roughly this, and therefore the natural log is roughly n log n minus n. This is going to be the form that we use it most often, but we're also going to want to know these others here. Okay. Any questions on that? All right. Keep this in mind, but remember also these other two. Now we're going to use this and apply it to the multiplicity of a large Einstein solid. And we'll see how well we're able to see the chalkboard here. I'm kind of skeptical. I think I'm going to just turn it back around to this here. You can see it straight on. Okay, color correction looks pretty good. Okay. So, first we've got to remember what the formula for the multiplicity of an Einstein solid is. And remember, the meaning of the multiplicity is the number of ways the system can be arranged at the micro state level for any given macro state. And again, a macro state is going to be large-scale measurements where maybe how much energy total, how many units of energy there are, how many oscillators there are. When we get to gases, we'll deal with temperature, with volume, with pressure. Those are macro states. The micro states deal with what is the energy, the specific state of every individual particle in that system. But most of the time we simply don't care. But those will affect how the system behaves. So first let's remember the formula for the multiplicity of an Einstein solid. So equation 2.9 gave us for an Einstein solid with N oscillators. Remember that means N over 3 atoms. Each atom has 3 oscillator directions. And Q units of energy, Q standing for quantum. Q quanta of energy. We've got that binomial notation here. The multiplicity is, in the upper part, Q plus N minus 1. We have Q plus N minus 1 things, choose Q. It's a way of saying it, awkwardly. And the formula becomes this factorial, Q plus N minus 1 factorial, over Q factorial times N minus 1 factorial. Okay, and that is true. Let's make sure here. I think that we had that's the general form. Let's only consider it in what we're going to call the case where there are a lot more units of energy than there are oscillators. So each oscillator on average will have several units of energy to it. So if Q is much greater than N, we call this the high temperature limit. This holds true in every case, but if Q is much greater than N, then and Q and N are both large, there. Actually, I'm sorry, I haven't yet applied this rule here. So far, I'm only applying the fact that Q and N are both large, and because that's true, then that minus 1 here and here doesn't really make any difference when we take the ratio of them. Okay. Now, later on I'm going to apply this fact I just stated that Q is much greater than N, and this is called the high temperature limit for reasons that will become clear later. And I'll apply that later. Okay. So now I want to apparently make a dramatic pause. Now I want to take this and I want to get it into a form that is simpler to work with. We never like having factorials around here. It's much nicer if we can use Stirling's approximation and turn those into logarithms or exponentials or so on like that. So luckily, that's what Stirling's approximation lets us do. Let me see here where I can, I'll just start up here. Okay. Now, taking this from this here, let me factor out, let's see. Hold on a second, I realized I approached this in a different way from the way the book did it. Okay. Let me continue here for a moment. Let me show you more strictly how we can get rid of that there. Because it's not always clear when you've got factorials running around whether it's safe to ignore a difference of 1 on that. I can show you exactly. Okay, so we can put this into form q plus n factorial. Q plus n minus 1 factorial is q plus n factorial over q plus n. Think about that. If q plus n minus 1 factorial is q plus n minus 1 times q plus n minus 2 times all the way down to 1. Just keep subtracting 1. But q plus n factorial is q plus n times q plus n minus 1 times q plus n minus 2 times all the way down to 1 as well. So you can see that the only difference between these is that factor of q plus n. So if I take q plus n factorial and divide by q plus n, I've got q plus n minus 1 factorial. So that numerator becomes this ratio here. Now I can do the same thing. Let's see. N minus 1 factorial is n factorial divided by n. Now that's in the denominator, so I've got here, let's see, I've also got 1 over q factorial. Let's leave that there. 1 over n minus 1 factorial, by the same logic, is n over n factorial. There we go. Okay, and work that out for yourself. Now, what I have is, let's see, let me rearrange these so all the factorials are in the first term. So I have q plus n factorial over q factorial n factorial times, let's see, n over q plus n. Q and n individually are large numbers. So q plus n factorial, q factorial, n factorial, all of those are very large numbers. N over q plus n is again a large number. So if I have very large numbers times large numbers, I can drop the large numbers. That's a property of the very large numbers. So I can just take that there. Just to save myself space, I'm going to erase what I just derived and write it over here. It comes out to, the book makes it look like you simply dropped a difference of 1 in these factorials. But it's best to see why you're able to do that using rules we've already learned. Okay. So, writing down what I've just done, that approximation. Let's take the natural log of both sides. So natural log of omega is natural log of this ratio. Now I've got a ratio and I've got products in the denominator, so I've got three terms. Natural log of q plus n factorial minus natural log of q factorial and minus natural log of n factorial. Okay. From that last term in Stirling's approximation, the last step of that, I know that if I have n as a large number, then the natural log of n factorial is approximately n log n minus n. The same thing applies for q, the same thing applies for q plus n. So for each of these, I use that last form of Stirling's approximation. So here I've got, whatever it is factorial. So q plus n times log of q plus n minus q plus n. That's the first term. Now do the same thing for q factorial and for n factorial. I'm going to wrap this around down on another couple of lines because I need to save myself space. So minus q log q plus q, because I've got a minus sign overall, and then minus n log n plus n. Okay, now without doing too many extra steps, see here I've got a plus q, and here I've got a minus q. Here I've got a plus n, and here I've got a minus n. So that term cancels out those two terms there. All right. The next thing I should do, let me rewrite this. And I've got n minus q log q minus n log n. Okay. Now we have to, we also don't like to have the log of a sum of things, sum or differences. Log of a product is great because we can immediately break it up into two separate logarithms. But the log of the sum, we can't. But there is an approximation for the log of 1 plus, let's say, x, where x, the absolute value of x is very, very small. In that case, we can use the Taylor expansion, and we can get rid of the logarithm altogether. Let me show you here. I'm going to take this. Let me move the camera over a little. Okay. So what I want to do is to get this into a form where I have something like log of 1 plus x, where x is much less than 1. So how can I do that? All right. What I can do is, because q and n are both large, and I've already said that q is much greater than n. This is called our high temperature limit. Then, if I can come up with a ratio of n over q, and q much greater than n, then I've got something much less than 1, and that'll be nice. So let me factor out a q inside the argument. So now the argument is q times 1 plus n over q. Now I've got this 1 plus something much less than 1, and that's going to be where I take my approximation. Of course, I've got a product now. Okay. So here, starting from, you recall Taylor expansions? This is in some parts of calculus where if you have any kind of a function, Taylor expansion deals with if I want to, maybe the function's hard to deal with on its own, but for some small region around some point on the function, you can have that function be approximated by a series of other functions where you've got the function, the value of the function at that point, which is just a number, plus something involving the first derivative of the function, plus something involving the second derivative and the third and so on like this. And presumably each one of those extra terms is smaller and smaller and smaller, and then you can ignore most of those. So, this is in the back of the book as well, but then because of that, it turns out that, let's see here, the natural log of 1 plus x is about equal to x, as long as x is much less than 1. Actually, as long as the absolute value of x is much less than 1. So, in our case, that means natural log of 1 plus n over q, well, since q is much greater than n, this is something much less than 1. And so that's going to be approximately n over q. Okay. So now we've gotten rid of most of the ugly terms in this. We're still left with some logarithms, but now it's just a log of q. We've also got a log of q and a log of n there. So let's put all of these together. I'll put it to the next board. Okay, so we've got q plus n times what was the natural log of q plus n. Now we've approximated that as log q plus n over q minus q log q minus n log n. Now this is kind of nice because we've got much simpler logarithms. Let's expand this here. Let's see, let me make sure that's what I want to do. Yes, it is. Q times n over q okay, and now I'll put these other two logs on the next line down. I might as well go and use the space. here, those two Q's cancel out, and I've just got an N, which is nice. Q log Q minus Q log Q. And I've got N log Q minus N log N. Well, at least I can combine terms there. So taking the terms that are multiplied by N, I've got N times N times log of Q minus N times log of N. There. Plus N plus N squared over Q. Okay. I've got a difference of two logarithms, so what can I do with them? Right. So I take N times log of Q divided by N, which by the way is nice because remember in this high temperature limit that we're assuming, Q is much greater than N. Well, that doesn't really get us anything here. But think of this. If Q is much greater than N, well, Q is much greater than N squared over Q is a very small number. So that's about equal to 0, at least compared to these large numbers here. Okay, so I can drop that last term because it's insignificant compared with N or N log Q over N. Now remember that this is the logarithm of the multiplicity. I really want the multiplicity itself, so I exponentiate. Remember, if I exponentiate some two terms added together, it's equal to the product of e to that first term times e to the second term. So I've got two terms here, two exponentials. N log of q over n is equal to log of q over n raised to the nth power. I think I'm going to need more space up here now. Okay, that should be far enough. So I've got e to the natural log of q over n raised to the nth power. And this is nice because now I've got the exponential of a natural logarithm, so those will go away, times e to the nth power. These are both raised to the nth power. I can bring the e inside the term here. There. Now, this is the multiplicity of an Einstein solid for a large Einstein solid in the high temperature limit. Okay, so it's a large system, so we were able to use Stirling's approximation, and and we're assuming that there are a lot more units of energy, quanta of energy, than there are oscillators, and this will be called, as we'll understand later, the high temperature limit, because this happens when it gets to high temperatures. This, it may seem like I'm putting a lot of conditions on that, but any solid we come across in everyday life is a large Einstein solid. It's got maybe some fraction of a mole of particles, so therefore certainly of oscillators. So we commonly come across the large systems, and the high temperature limit is really not anything that's too far out of the ordinary either. So this is actually a useful formula. Notice how simple it comes down to. We don't have any factorials, and now really no logarithms either. QE over n, all raised to the nth power. And now we're going to use that in finding out how the Einstein solids behave, at least at fairly high temperatures. Okay, so next I'm going to look at how two large Einstein solids at a high temperature limit, how they behave when they're interacting and they can exchange energy. Okay, now that we have a simple formula, the interaction between two of these becomes even simpler still. So let's say here's an Einstein solid A, and here's solid B. Each one of them has some number of oscillators. Each one has n oscillators. And A has QA units of energy, and B has QB units of energy. The little wavy line means radiation. They can exchange energy. Energy is exchanged with the little wavy lines, back and forth. But they are insulated from the rest of the world, so that the total amount of energy between the two of them is conserved. Okay. So the total units of energy Q is just the sum of QA and QB. Okay. Now, let's see where to start with this. Whenever we have a combined system, if you have part A and part B for the system, the multiplicity of the entire system is just the product of the multiplicity of A and the multiplicity of B. Like that. So this is for the combined system, or the total system. Now, for each one of these, if this is an Einstein solid in the high temperature limit, we know, I won't bother writing the approximation symbol, but it is an approximation, that the multiplicity of A is E times QA over N, all raised to the nth power. And the same thing for B as well. All right, so let me write down the product of these two. So the multiplicity of B is E times QB over N raised to the nth power. We're labeling them each with how much energy each one has, and I'm not labeling N sub A and N sub B because I've started off saying that each one has N oscillators itself, as you can see this here. Let's combine this. We've got, if we put this all inside one set of parentheses raised to the nth power, I've got E squared QA, QB, all over N squared, and raised to the nth power. Now, I can factor out the terms that are that don't have any subscripts. Which would be E squared over N squared to the nth power, which is more simply E over N to the 2nth power, times QA QB to the nth power. All right, now at this point, I'm going to want to get rid of, well, I've got QA and I've got QB. I don't need to keep track of how many quantum energy B has, because I know QA plus QB is equal to the total. So if I know the total amount of energy, and I know how much A has, then of course I'll know how much B has. Here it's going to be convenient, though, to define another term. We'll just call it X, where X is QA minus QB over 2. And I should really put, that's the definition of X right here. So it's the difference between their energies divided by 2. You could even write it out as delta Q over 2, but keep in mind, this is what it is here. All right, this will mean then that X tends to be much less than Q, which is going to be useful in approximating. Now, if you do a little bit of algebra, and it takes about 3 or 4 lines, you can find that this means QA, you can solve for QA in terms of X, and you can solve for QB in terms of X. Because, well, let me think here. We've got QA and QB, and we've got X, and we have Q. So, depending on what you want to call your unknowns, if QA and QB are your unknowns, you can get them in terms of X and Q. It's equivalent. 2 equations, 2 unknowns, and you'll come up with QA equals Q over 2 plus X, and QB is Q over 2 minus X. And again, you can prove that by doing about 4 lines of algebra. Okay, so let's rewrite this multiplicity formula that's now in terms of QA and QB and put it in terms of Q and X. This way, we've got Q, which is the total amount of energy, total number of energy units, and only one arbitrary kind of abstract term, which is X. Turn my camera over a little. Okay, so the first term, E over N to the 2nth power. Now, QA, QB nth power becomes q over 2 plus x times q over 2 minus x to the nth power. Okay. Well, it looks like if we multiply these two together, now we're going to get some squared terms, and it'll be a bit simpler. Also, keep in mind I've got this, these are exponentiated right now, so let's take the natural log. Let's see. Making sure I keep it straight when I need. Oh wait, I haven't gotten to that part yet. I can just multiply this first. Okay, that's simple enough. Q over 2 squared minus x squared, all raised to the nth power. Now I take the natural log of both sides. I think I'm going to leave this without doing anything yet. Now, I'll focus my attention on this last term. Okay. Remember that x is much less than q. So, just like before, I'm going to want to get it where I've got natural log of 1 plus some small number much less than 1, or the absolute value is much less than 1. And because x is much less than q, if I've got an x over q inside here, then I'll have exactly that, and I can use an approximation from the Taylor expansion. So I'll just work on this last term. Okay, let's see. If I factor out q over 2 squared, all right, then I've got 1 minus, let's see, x over q over 2 quantity squared, which would be two x over q squared. There we go. So I've got 1 minus this here. All right. Since q is much greater than x, or x is much less than q, x over q is much less than 1, and this approximation from the Taylor expansion says that, pay attention to the sign here, this will be, let's see, I want to break that up first. So natural log of q over 2 squared plus the natural log of this last term, 1 minus 2x over q squared, all to the nth power. The approximation I've talked about says that this will be approximately negative, that sign will attach to this here. I needed to do one more step first. Let's take this exponent, multiply it out front of both of these natural logs. There we go. Much better. Now I'll have, this will be n times, instead of log of 1 minus this small number, it'll be simply negative that small number. Negative n times 2x over q squared. Okay. Now, I can combine, let's see here. I can re-exponentiate, so in natural log of q over 2 to the 2nth power. Minus this here. N times 2x over q squared. Okay. I'm going to need to go to the next line here, the next board to, I'll have to combine it with this first logarithm, and then I'll exponentiate to get the multiplicity. It is going to come together in a fairly simple equation, you'll see. Okay. There it is in context. Now, let me see. I've done things a little differently than I had in my notes. Oh, that's fine. I'll combine these two. Okay. Yeah, all right, that's good. I exponentiate. Take e to both, e raised to both sides. In my first term here, I'm going to get e to the natural log of this, which is just, well, this. EQ over 2n raised to the 2nth power times e to this second term there. But what do we have? With x being some variable, what we have is a Gaussian. This here is the form of a Gaussian. As x varies, you see that this will peak. This will have its maximum value where x equals 0. And when x is 0, e to the 0 becomes 1, which means that this here is its maximum value. That. So as a function of x, the multiplicity peaks at x equals 0. And the maximum value is this first term here. because where x is 0, e to this term here is 1. But we're not interested in x. We don't measure x. What we've got is Q, the number of energy units. And we put it in terms of Q, we get a Gaussian as well, but shifted. Where, as you can solve, the peak is at Q over 2, half the total. And you have some, this being a large system, it's got a narrow peak. And the maximum value, again, is the same thing. EQ over 2n raised to the 2n power. Okay, so it peaks strongly around Q over 2, which means, I'm sorry, I wanted to plot this not in terms of Q, which is a constant, but the number of units of energy that A has. That's what I mean. So if both A and B have the same number of oscillators, you're most likely to find a system with each having half the total energy. A has half the total energy, and therefore B will have half the total energy. Got a sharp peak there. So, we're finding now that while we had gone with small systems, we saw a histogram that looked more or less bell curve or Gaussian shaped. Now with a large system, we can prove it actually is a Gaussian, because we have the formula for a Gaussian right here. E to the negative some variable squared. And that's the form of a Gaussian. So, our statistics have given us this nice form here, and we're going to wind up making use of that because the second law of thermodynamics really is a statement of probability, and it's going to drive the system towards thermal equilibrium and other kinds of equilibrium too, where it's going to want to come to equilibrium at whatever this state happens to be. And that's going to be what we get to on beyond this. Any questions on this? All right.